Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of vehicle loans, and we're going to try to predict if a given loanee will default on their loan or not. And we have 41 different columns here, so 40 different potential features, and at the end we have a binary column called loan default, which we'll be trying to predict. So let's go ahead and create a new notebook, and I will just set this notebook up real quick. Alright, so we're going to be using NumPy and pandas for working with the data. We'll also, for our pre-processing, we'll use regular expressions, the train test split function, and stratified k-fold. This actually is not pre-processing, but I'm importing it here. This will be used to evaluate the model, as we are not given answers to our test set. And then we have the min-max scalar and standard scalar, and I'll try it with both and see which does better, but that will be for scaling the data. And then our actual model will be logistic regression. So let's go ahead and import all of those imports. And then, like I said, well, we have two different sets of data, the train set and the test set. The train set has a label column, the test set does not. So let's import them both. Train.df is going to be train.csv, and we can load it in with pandas.readcsv, paste in the file path, and we'll do the same thing for test.df. Just change this to test. Alright, and once we load those in, just take a look at them. So train.df, 41 columns. You can see there's a variety of different types of columns here. Some of them are object columns. We also have a number of them that are actually categorical columns encoded as numbers, like these IDs. And then there are a good number of numeric columns as well. At the end here, all the way at the end, we should have a loan default column, which is signifying if a given person defaulted on their loan. So 1 means they defaulted, 0 means they didn't. And then let's look at the test.df. So here we have 40 columns, and that's because at the end we do not have a loan default column. So here we'd like to make some predictions for test.df. Let's say you're developing a model and you're only given train.df to train the model on. And then someone comes along with some new data and says, I'd like predictions made on this. They're not going to give you the label column. So we want to find a way to evaluate the model without being able to compare the test results to actual answers. And so we'll use stratified k-fold for that. So it's basically a way, it's like k-fold, but it tries to mimic the class distribution of the original dataset. So it's maybe more realistic in the classification setting than just regular k-fold. Alright, so I also want to get a little information on each of these datasets. So traindf.info, and we can see the kinds of missing values here, as well as how many object columns we have, which are 6. And it looks like I only see one column that might have some missing values here. And so let's look at test.df as well. Let's take some info. In here, yeah, it's looking like maybe this is the only column with any missing values. So that's interesting. I'd like to explore that column more. Usually when you have like maybe one column with missing values, it might not be improperly entered data, because all the rest of the data, especially with so many examples, has been entered properly. It's possible that this missing value actually means something more significant. So let's get into pre-processing. So I want to take a look at the actual missing value counts of train.df. So .isNA will give us the matrix of trues and falses, where true denotes a missing value. So if we sum over the rows, we'll get the total number of missing values in each column. And we have 7,000 missing values in employment type. So let's look at what kind of values we have inside employment type. So we'll take the column employment type and then find the unique values in it with .unique. And so we have salaried, self-employed, and missing. And what's interesting here, I may under different circumstances, just fill this in with the mode of the column or give it its own value. But I think it's important to understand why we have this value. In test, let's look at test df. We have also some values there. So I might assume here that this missing value means the person is unemployed, because we have only two options for employment, and no other column has missing values. So I think it's safe to assume that these missing values mean the person is unemployed. And so I want to make sure that we go and encode that properly. So let's make a function called preprocess inputs. It's going to take in a data frame. It'll make a copy of the data frame to start off, and then we'll return the data frame. So right now all this does is copy a data frame, but any pre-processing steps we can add into the function and see the result below. So I'll call xtrain. That will be the processed version of train.df. So we'll call preprocess inputs on train.df. And if we look at xtrain now, it should be the same as train.df. But now let's go in here and fill in those missing values. So let's actually say encode missing employment data, employment values as unemployed. So to do this, all we have to do is take the employment type column and call fill.na on it, which will fill any missing values with whatever value we plug in. And I'm just going to plug in unemployed. Alright, and then I'm going to set that to the original column, and let's see what happens. Now we'll call this function on xtrain, and now xtrain looks the same, but if I count up how many missing values we have in it, I can sum over both the rows and columns to get the total number of missing values. We should have no more remaining missing values. Oh god, I'm trying to sum the whole data frame. I forgot .isNA. Alright, so we have no more missing values in the dataset. And if we pass xtest through here, we should also get the same thing. So xtest is just going to be testdf passed through our function. So xtest.isNA has no more missing values either. Alright, now the next thing to do, I want to start filtering it through the columns. That's usually the first thing to go for. There might be some columns in here we don't want to use. For example, the unique ID column is a clear one to drop. It actually says in the title it's unique, and a unique column is not useful in making predictions because there's no similarity between any of the values in the column. So it's basically, there's no information there that connects different training examples to each other. So let's go and drop that. Drop the unique ID column with df equals df.drop unique ID, and we're dropping from axis 1, which is the column axis. Alright, and then, so if we run this, take a look, unique ID is gone. Now what I'd like to do is, I'd like to look for high cardinality columns. So if we had a lot of time on our hands and a lot of resources available to us to make these predictions, we may consider leaving on these high cardinality columns. A high cardinality column is just a column, a categorical column with a high number of different unique values in it. So these can be problematic when we're dealing with one-hot encoding because they can add a whole lot of new columns to your dataset that can really slow down the performance of your model. And since we're just doing this as a sort of tutorial exercise, I'm not going to include these high cardinality encodings because it will just really slow down the model. So let's take a look at some of these. What I'm going to do is create a dictionary that's going to map a column name to the length of unique values in that column. So I'm looking at xtrain subcolumn dot unique, and then I'm taking the length for every column in, and now I want to specify which columns we want to look at. So I actually want to look at all the categorical columns, and I can't use an expression to express this because we have some as numeric and some as text. So I'm going to just go through and grab these. We have some ID columns, which are definitely categorical because uh, they're not numeric. They're not on a continuous range. These are unique identifiers. So we're going to grab these, and then the pin code ID as well. I'm going to leave date of birth. That's not a categorical column. Then we have employment type. This is categorical. We actually know how many we have in there already, but I'll leave it on. Then we have some more IDs right here. And I think there's just one more in here, which is this one. I think all the rest are numeric. Just double check that. These are all like counts and balance amounts. Amounts, counts, yeah. And then at the end, well, we have this, but these are really sort of two numerics in one. What I'm going to do is go through in these columns, take out the years, put it in its own column, take out the months, put it in its own column. So here we go. Let me just clean this up. Just turn this into a list, like this. I think that's it. Okay. So we can see how many unique values we have in each categorical column. Now, so many of these are reasonable. Like these are fine. These 2 digits are fine. Even if we had some in the hundreds, it'd be fine. But there are some here in the thousands, and we are sort of dealing with a limited set of resources, so I'm going to drop these columns. Now, if we had a lot more time and resources on our hands, then I would probably keep these in. They might offer some useful information, considering we have 230,000 examples, and there's only 6,000 unique values among those examples. This actually probably contains some useful information. However, like I said, because we're dealing with limited resources, I'm going to drop them just so we don't slow down the model too much. So supplier ID, current pin code ID, and employee code ID I'm going to drop from the dataset, just because they have too many values in them. And the reason I just want to show you with pandas.getDummies, this is a function that can give you the dummy columns for a given categorical column. So for example, if we do manufacturer ID, not df, it should be xtrain. Then each, let's actually use employment type, be better. Yeah, so each categorical value gets its own column, and then each example is represented as a one-hot vector, where the 1 corresponds to the original value of the example. This is fine when you have a small number of columns, but now if we try doing current pin code ID, I mean, it will load up, but it's going to take a while. And that's because it actually has to create 6,000 new columns, one for each unique value. And so here it is. So 6,698 columns. And if we just put this on the end of our data frame and try to train a model on this, it's going to really impede the performance. Well, maybe not necessarily the performance, but at least the speed and the computational power that is needed to make predictions. So let's go ahead and drop these. Okay, it's 3 of them: employee code ID, current pin code ID, and supplier ID. So let me just get this in a list. Alright, and I will go and grab this and put it here. I'll say drop high cardinality columns. df equals df.drop. Paste in the list. We're dropping from axis 1. And there we go. So now we run this. We no longer have those columns on our hands. So all the remaining, if we look at this now, we don't have, hold on, let me just remove them from here. Last one here. You can see the remaining categoricals have a very fair number of unique values. So we won't add too many new columns onto our dataset. Alright, so now let's move forward with some other pre-processing steps. So the next thing I want to do, there's like sort of three more things I gotta do. One thing, I have to deal with these date columns. I have to encode them in some meaningful way. Next thing, I have to deal with these columns, and like I said, I'm just going to take out the years and the months and put them in their own columns. And the last thing I'd like to do is one-hot encode the remaining categorical columns. So for that, I'm going to create three new functions. I'll do them one at a time. First, we're going to do encode dates to deal with the dates. And the encode dates function is going to take in a data frame and a column we'd like to encode. And basically what this is going to do is it's going to take the date, take the year out of it, put that in its own column, take the month out of it, actually this is month, put that in its own column, and then take the day out of it and put that in its own column. So you can see here that this is encoded in a day first encoding, so we have the day, month, year, and so we have this function pandas.toDateTime, which is a very useful function for dealing with dates. Let's say we take in one of these. We take in a string and we encode it. We call toDateTime on it. This actually will return a timestamp. Actually, it's a datetime object, and we can call .year on it to get the year, .month on it to get the month, and .day on it to get the day. However, this can confuse it because it doesn't actually know, but from looking at this, which is the day and which is the month. And because we are doing day first here, we actually want to go in and include day first equals true. Now it probably switched these internally, so now it knows for sure. And if we pass this in, you can see it does it as well. It knows the day goes there, the month goes there, and the year goes there. So this is useful because now we can just type .year and send all the year values to its own column, .month to send all the month values to its own column, and .day to send all the day values to its own column. So let's include that in our function here. What I'd like to do is take in a data frame and a column, and we'll start by creating a copy of the data frame so we don't modify the original one in place. And then we're going to set the column to using pandas.toDateTime, set it to a column of datetime objects. So you can pass in a whole column as well to datetime, and it will just cast across the whole column. And we want to include day first equals true. So once we have it as a datetime object, we can go and get the individual year, month, and day features out of it. So we can we want to give these columns new names, but I want to include the old column name in the name, so I'm going to say column plus year. So we'll have, let's say we pass in date of birth, then this will become date of birth year. And that'll be the original column with a function applied to it, a lambda function that takes in, for a given x here is just one of these, x will become x.year. And since it's in datetime form already, that's fine. Now we'll just do it for month and day. So here and here becomes month, and here becomes day. And then once we've taken off those 3 bits of information, we don't need the original column anymore, so let's go ahead and drop it from axis 1. And we'll return df. So here is our function. Let's go in and say extract date features. Now we have 2 columns we'd like to do this for, the date of birth column and the dispersal date column. So what I'll do is say df equals encode dates, df, and column equals, I'll just copy it, date of birth. Then we're just going to copy this whole column, this line over, and instead put in dispersal date. So it's going to do it once for date of birth, once for dispersal date. And if we take a look at this now, it might just take a moment. Sometimes the toDateTime function can be a little slow. And I think this can be sped up by passing a format in. But I guess I could try it. See if we can get some more speed on it by specifying a format. Format just means we actually hard code in the way that the date is formatted. So like this. We just in here include format equals, and then we'll substitute these for the identifiers for them. So let's actually get that. So if we look at toDatetime, the docs for it, you can see these are a list of formats from Python. So we need the month as a 0 padded decimal number, the year without a century as a 0 padded decimal number, and the last one would be the day of the month as a 0 padded decimal number. So day is %d, month is %m, and year is %y, all lowercase. So in here, we're going to we'll replace the year with %y, replace the day with %d, and replace the month with %m. And I guess we don't need day first equals true since we specified the format explicitly. And you see it did finish, but I just want to see if that actually speeds things up. Running this again. I'm not sure if it will, but we'll see. And so now you can see on the dataset at the end here, we have all of those columns now as their own columns, and they are already encoded as integers. Yeah, that looked a little faster. I'm not sure though. Okay, so what to do next? Okay, I want to work on these ones. So like I said, I'm just taking out the years and months and putting them in their own columns, sort of like similar to what we did with the dates. So I'll call this encode durations because this is a duration coming in. And that will be also taking a data frame and a column, creating a copy of the data frame, and then at the end, well, we won't get there yet. Let's think how to do this. Okay, with this one it's not so easy because we can't just convert it to a datetime object. We're probably going to have to use regular expressions. So when using regular expressions, I love to use this website, regex101, which allows you to basically put in a string and then capture elements of the string using a regular expression up here. It's a great way to test out regular expressions. So let's go and grab this one, just as a sample. And we want to write a regular expression that can capture the number of years and capture the number of months. And for this, we're going to want to use positive look-ahead statements. So basically, that looks like this. You write it like this with a parentheses, and then inside you put a question mark and an equals. And that basically says, always look ahead for the following characters. We're typing YRS. And you can see we put something before it now. And we can ask to see any digit characters that come before YRS. And you can see it has targeted that digit using the positive look ahead. Now similarly, we could change this to MON, and then it would target any digits that come before MON. And so this is a great way to capture. I mean, this is doing the job. By adding this little plus sign here, this allows us to put any number of numbers here, and then change back to YRS. You can see. So this will work. Let's grab that and use that in our function. So I imported regular expressions at the top. That's the RE library from Python. And then we will basically create two new columns. I'm going to I'll call one of them column plus years, like that. And that's going to be just the years part. So that's going to be the original column with a lambda function applied that takes in an x and returns re.search, which will search x for a regular expression that we specify, and the expression we want is the one we just got, and we're searching x. And we also, after this, will actually return a match object, so we want to get the string value that it found with .group of 0. And this will return the result of our regular expression search for every x in df subcolumn. Okay, and then after that's done, I want to turn it into an integer column with as type numpy.int, and we'll do the same thing for the months. So only difference here is this is MON, and this here is MON. Alright, and now let's try this down here. We'll say encode, we'll say extract duration features. And df equals encode durations, df column equals, and so there's two of them here. One is average account age, and then the other one is credit history length. Alright, so run this and take a look. We actually got an error because I forgot to return df at the bottom of here. Let's try that again. Alright, so let's take a look. Here it is at the end. We have the years and the months that originally came from those columns, which I actually forgot to drop. We still have them here so we can see. We have 1 and 9 and 3 and 3. So over here we have 1 and 9 and 3 and 3. So I would like to include in this function, after we've finished it, let's drop the original column since we no longer need it. Alright, so the next thing to do is the one-hot encoding. So for that, we just need to take our categorical columns, and then we need to encode them. So I'm going to create a new function called one-hot-encode. This will take in again a data frame and a column. We'll create a copy of the data frame, and then we're going to create some dummies. So I showed you pandas.getDummies earlier. It basically just sends each unique value to its own column, and we're going to do that for every unique value in df subcolumn. We can include a prefix at the beginning of each column name to sort of get so we know where these dummy columns are originally coming from, and I'm going to include the prefix as the actual column name itself. So that will work. Then once we have our dummy columns, I'd like to add them to our data frame with pandas.concat. So we're going to concatenate the original data frame and the new dummies side by side, so x1. And then we will drop the original column from which we created dummies. Alright, and return the data frame. There we go. So down here, say one-hot encode categorical features. They are all nominal features, which means there's no ordering between the values in them. So that means we can just go ahead and one-hot encode them. So let's go and grab them. So we have branch ID, manufacturer ID, employment type, state ID. These are some of them. So I'll say for a column in these ones. And then I think there's one more in here, which is this one. And I'll just go and clean this up a little. Oops. Alright. So for each of these columns, we'll call our one-hot encode function. Pass in df and the column that we're iterating through. Alright. And so there we go. Let's actually run this and take a look. Alright, it's finished. And we can see our data is basically completely pre-processed. The last thing I'm going to do is scale the data, but before I do that, I want to check xtest, because sometimes an issue arises with the one-hot encoding, which we need to address. So you can see the issue has arisen. So we have 176 columns up here, and only 174 in xtest. So the issue is, well, for one, we have this single column here. Actually, where is it? It's somewhere here. Lone default, which we know is not on. Here it is, lone default. We know this column isn't on xtest because it's the prediction column. It's our label column. We don't have it associated with this. However, there's at least one more column here that's not present on xtest. So we have to do a little adjustment. And the reason this happened is because we one-hot encoded each one independently. So we took the unique values in xtrain and then sent those to their new columns, and then we forgot about that and looked at xtest and took those unique values and sent them to their own columns. So if there were some unique values that were present in xtrain that weren't present in xtest, then we're going to get extra columns in xtrain. And vice versa, if there are some columns that are present in xtest, unique values that are present in xtest that weren't present in xtrain, we're going to have some extra columns on xtest. So we can figure this out. I'll just copy in this markdown block. We're going to adjust the xtest dummy columns to match xtrain. So what I'll do is say for each column in xtrain.columns, if the column is not in xtest.columns, so we're comparing the xtrain column to an xtest column, then we'll print out the column name. And you can see there are actually 3 columns that match this problem. Lone default doesn't really count, so actually let me go ahead and drop that. I'm going to send load default to ytrain, so that will be train df sub lone default. And then xtrain will just be, we'll just drop lone default from xtrain since we saved it in ytrain from access 1. Alright, now we run this, we just get 2. So there's 2 columns in xtrain that are not in xtest. Similarly, let's do the same thing the other way around. Let's check if there's columns in xtest that are not present in xtrain, and there's 1. So the one-hot encoding has these sort of discrepancies here. So what I'd like to do is create a function that can adjust xtest based on what we have in xtrain. And the reason we do it that way is because if we're ever given more data in the future, we can always use this function to sort of fix up the columns to match our original training set. So I'm going to call this function adjust columns, and it's going to take in xtrain and xtest, and it's going to return just xtest, new version of it. So what I'll do is I'll create these 2 new lists called train columns. That will be these ones, the columns in xtrain that are not present in xtest, and then I'll create this new list called test columns, which will be this one, so the columns in xtest that are not present in xtrain. And then we want to get the xtrain columns that are not present in xtest. So I'm just using this loop I have here, and instead of printing them out, I'm going to append the column to train columns. And we'll do the same thing for the other ones. For this one is the xtest columns that are not present in xtrain, and this just is for this is just this is the same as, wait a minute, I did it wrong. This one should be changed. xtrain.columns and xtest.columns. So train columns, also this is test columns that append. Alright, so train columns will be these 2, and test columns will just be this one. And once we have these, we're going to remove the test columns from xtest. And that's because these ones don't matter. Because even if we have unique values in the test set that weren't present in our original training set, we can't use them because the model doesn't know how to handle them. The model has only seen the values associated with the train set. So we can't pass in new values in the form of columns with categorical variables unless we want to retrain our model and use this new data as training data. But again, for that we would need labels associated with them, and we don't have that. So we have to remove these columns. So what I'll do is create a copy of xtest so that we're not modifying it in place, and then we will just drop those columns. So xtest equals xtest.drop test columns from axis 1. Alright, and once that is done, we then have to deal with the other ones, the train columns. We'll say add train columns and fill them with zeros. So since there's no data there, I'm just going to fill it all with zeros. But this is basically just putting in empty columns into xtrain, into xtest that weren't because there are columns in xtrain that need to be in xtest so that we can pass the input into our model, but they aren't there because the one-hot encoding did not capture them. The unique values associated with them were not in xtest. So what we'll do is for every column in train columns, so for each of these ones, we need to make sure that these are present in xtest. So we're going to get the indices for them. For each column, we'll get a column index. The column index will just be the position in the data frame columns where it shows up. So we want it to retain the same order as well. So the way we can get this is take xtrain.columns, which is just an index of the columns, and I want to turn it into a list so that we can call .index on it and pass in the column name. And this will return the index of the column. Then we can take xtest and insert with .insert. We want to specify a location to insert. That will be our column index. That's where we're inserting. Then the column name will be column, and the value we're inserting is 0. And that will be inserted for all of the entries. And that's it. Then we return xtest. So then xtest equals adjust columns, passing in xtrain and xtest. And we get a problem. Oh, sorry, this should be called value actually. Okay, let's take a look. Alright, so we have 175 in each, so it's looking good. We can verify that it's doing properly by taking the columns of xtrain, checking if they're equal to the columns of xtest, and then checking that equality for all examples with the .all. And that is true. So all the columns in xtrain are equal to the columns in xtest. Alright, and now I guess we'll just scale the data. There's nothing left to do. So we can use, I imported two scalars. I have a min-max scalar and a standard scalar. They're similar but different. The min-max scalar will take the minimum and maximum of each column and set them to 0 and 1, so it'll squash the data down to be strictly between 0 and 1. And the standard scalar will shift and scale the data so that the mean of the column is 0 and the variance is 1. So most of the training examples will most of the values will lie between -1 and 1. So both are used to standardize the columns of the dataset, and that can improve the performance of many models. It's good practice to do. So let's use the min-max scalar to start, and I'll fit the scalar just to the train set, because again we want to sort of pretend we only have access to the train set. Once we have the fit, we can transform both xtrain and xtest using the fit. Scalar.transform will accomplish that. Here in the top we pass in xtrain, and here we pass in xtest. And this transform function returns a numpy array, so I'm going to turn it back into a data frame after it's done. I also want to keep the indices and columns the same, so index equals xtrain.index, columns equals xtrain.columns, and on the bottom I want to set these to xtest instead. Alright, now we'll run this. Xtrain has now been min-max scaled, so there will be no values here that are higher than 1, and there will be no values that are lower than 0. If we call .describe on it, this will actually return the mins and maxes of each, and you can see there's 0 and 1 for each column. Okay. And I actually realized there's one in here with 0, which that's suggesting to me that maybe it's a column that has only one value in it. Let's double check that. Xtrain sub mobile number AVL flag dot unique. Oh yeah, there's only a single value in here. So this column is useless. There's no way to draw a difference between any of the two training examples. Similar to how we have the unique ID was useless because there's no way to draw similarities between the training examples. So let's go ahead and drop this up here. Unique ID and what's it called? This one. So I'll just include that in here. Okay. Now I think that's probably the only one. Let's just double check though. I'll get a column here. How can we do this? We can say, okay, length of column of xtrain subcolumn dot unique for every column in xtrain dot columns. If this length of unique values is 1, print the column name. There's actually two of them. There's dispersal date year. Okay, so after we encoded the year, it turned out that those were all the same. So what we can do is just drop that one after we encode the dates. Where is it? Up here. df equals df.drop, dispersal date year from axis 1. Alright, now we've dealt with those. Alright, so last thing, well, let's run this again since we made some changes. Alright, and just double check that the columns are right. Yep, they are still true. Okay. So now the thing to do is we want to start training. So I'm going to set this into separate this into two parts. First part, we're going to evaluate how our model is doing. Second part, we're going to make predictions for the test set. So evaluation with stratified k-fold. So like I said, stratified k-fold is a variation of regular k-fold cross-validation, which basically splits the dataset into a number of folds and then uses each fold as the it goes through each fold, using one as the test set and using the rest of the data as the training set. And if you do this for each fold, you can get a sort of overall sense of how your model is doing by evaluating it on separate subsets of the data. Now, stratified k-fold is similar, but it also retains it tries to retain the class distributions of the original dataset within each fold. So it's a more accurate measure when dealing with a classification task. So let's call our stratified k-fold object skf, and that will be stratified k-fold, which I imported from sklearn. We want to include the number of splits we're using, so I'll do 5. And then what we'll do, what I can show you, we can say for train index and test index in skf.split. So the .split function takes in our train set that we want to split. And when you're using stratified, you actually have to include the labels as well because it needs to know the class distribution. For each one, let's print out the test index. Alright, so for each of the 5 splits, we can see the portion of the data that's being used as the test set. And this is and these are meant to retain class distributions as well. So what I'll do now is go through each one of these splits, train a model on the rest of the data, and then evaluate it on the test indices here. And then I'll store the results in a list here called results. And so instead of printing this out, what I'm going to do is create a model, logistic regression, model, and we'll fit the model to the portion of the train set that is not in this test index, which is actually in the train index. So xtrain.iloc, or index locator, we're going to use train index as the row indexer, and then target all columns. That's going to be the input to our model, and then the labels are given by ytrain.iloc train index. So we're training only on the portion of the data that isn't the test indices for a given fold. So the train indices just contain all the rest of the data. Then what we'll do is store the result in result with model.score. Here we're actually using the train set again, but we're indexing with test index instead. And we're taking ytrain.iloc of test index. And then we will append the result to results. Right. And once that is done, what we'll do is go through our results and we'll enumerate it. So we'll say for I and result in enumerate results. Then we'll print out the number of the fold 1, fold 2, etc. And we will display the accuracy value for that fold. So I'll display it to 2 decimal places with a % sign, and format this with I plus 1, because I want it to start at 1. And then we will give it result times 100, since it's a percentage. And we can get an overall sense of how our model is doing this way. You can see we have an accuracy of about 75 to 78% for each across all the folds. So this is like a general idea of how our model is doing. Now, here I'll just paste this in. When we create our predictions, we can assume that they're 78% accurate. So we don't know for sure because we have no labels to compare them to. But assuming that the test data is representative of the training data, we can create our new model now, logistic regression, fit this model to the entire train set, and then get predictions using model.predict on the test set. And this should return predictions, a set of predictions. You can see them here. There's going to be like 100,000 of them, or however many test examples we have, that we can sort of safely assume are about 78% accurate. Alright, and the last thing I want to do is try this with a standard scaler and see if we have any differences. So standard scaler is just going to give each column a mean of 0 and a variance of 1, instead of scaling the min and max down. So I'll run that. Actually, I'll run the whole notebook again and see how this goes. Alright, it finished, and it looks like maybe it's a little worse. They're pretty much exactly the same, but I remember this one not being a little higher. So I'll probably just go back and change this to min-max. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.